Morning to Dr. Husnia. I'm from Group 5. My groupmates and I are going to be presenting about the summary of microstructure and mechanical properties of in-situ silicon carbide titanium diboride ceramic composite fabricated by reactive metal infiltration. I'd like to introduce my groupmates. I'll start off with myself. My name is Vinusha, anak perempuan Victor Tiruchelvam, and my teammates are Nurul Ilyana binti Razali and Nawal Nurkhailis binti Mustafa. Table of content. I'll be presenting the introduction and the problem statement. Meanwhile, my groupmate Nurul Ilyana will be presenting the objective and the process of ceramic fabrication. Finally, Nawal will be presenting the significant results obtained and conclusion. Introduction. Silicon carbide ceramics are regarded as an essential structural material due to its high hardness, superior corrosion resistance, outstanding thermal shock resistance, and high thermal conductivity. However, the low fractional toughness and weak mechanical properties severely limit its capability. Titanium diboride with high melting point, high elastic modulus, high hardness, and other properties was utilized as one of the particle reinforcement to improve the mechanical properties of silicon carbide ceramic in order to make them more usable. In addition, numerous studies have shown that titanium diboride particle reinforced silicon carbide ceramics has superior mechanical qualities compared to monolithic silicon carbide ceramics. Because of the high melting temperature, low self-diffusion coefficient, and significant covalent bonding of titanium diboride, fabricating silicon carbide titanium diboride ceramic composite using certain traditional processing techniques is extremely hard. Furthermore, the oxygen-rich layer on titanium diboride surface can encourage excessive grain development, resulting in porosity trapped inside the grain and poor fracture toughness. Hot pressing, pressureless sintering, and spark plasma sintering with or without additives are the current available manufacturing process for silicon carbide titanium diboride ceramic composite. The following techniques, on the other hand, have a high cost and high processing temperature as their common characteristics. The reactive melt infiltration method, which involves infiltrating silicon or aluminum silicon alloy melt into pre-synthesized porous titanium carbide, boron carbide, or multi-carbon carbide performs, has been highly used for fabricating silicon carbide ceramics in short time, low cost, and low processing temperature. The aluminum silicon alloy was chosen because it can lower the processing temperature, which is crucial for reducing thermal residual stress. Furthermore, as compared to pure silicon melt additions, the inclusion of ductile aluminum can improve the fracture toughness of silicon carbide ceramic composite. The composition of the performed and alloy melt may be adjusted to get the desired composition of silicon carbide ceramic composite. Silicon carbide titanium diboride ceramic composite might theoretically be made by mixing boron carbide powder with aluminum silicon alloy melt in titanium carbide perform. However, until today, the investigation of the RMI technique for creating silicon carbide titanium diboride ceramic composite has remained inclusive. The materials used in this experiment are titanium carbon powder, boron carbide powder, distilled water, and 1 nanometer diamond abrasive paste, whereas the apparatus used are ball mixer, freeze drying machine, cold press machine, furnace tube, jaw crusher, crucibles, electro discharge mechanism, X-ray diffractometer, scanning electron microscope, X-ray spectrometer, universal testing machine, and laser blade notching. Problem statement. Problem statement. In this research, by infiltrating aluminium silicon alloy melt into pressureless pure synthesized porous titanium diboride boron carbide mixture, certain silicon carbide titanium diboride ceramic composites were effectively synthesized. RMI response mechanism is extremely difficult to manage. Due to the incomplete interaction between the perform and the melt, certain byproducts are always present in the produced silicon carbide titanium diboride ceramic composite, which may be detrimental to their mechanical characteristics. In order to minimize the appearance of the byproduct, titanium diboride boron carbide mixture performs the reasonable titanium carbide weight ratios were designed so as to synthesize pure silicon carbide titanium diboride ceramic composite. Mechanical characteristics were examined and the microstructural evaluation was studied. The relationships between composition, microstructure, and mechanical behavior of these ceramic composites were investigated on this basis. Finally, the RMI was used to learn more about the synthesized pathway and fracture behavior of silicon carbide titanium diboride ceramic composite.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Elena binti Razali. My metric number is A175674. So my parts in this assignment are objective and process fabrication of ceramic. In this research, their objective is to understand the synthesis mechanism of the composites when an in-situ SiC-TiB2 ceramic composites was fabricated by infiltrating the aluminium silica alloy melt into pre-sintered porous preforms by different weight ratios of B4C over TIC. It is also to get the synthesis mechanism of the phase composition and the microstructure of the SiC-TiB2. There are three different categories that have been analyzed for materials and methods mentioned in this article. Firstly, materials preparation. In this preparation, the TIC powder, B4C powder, free carbon and B2O3 impurity had been prepared and mixed well with distilled water to get slurry and ball made for 12 hours. The variable change composition of X equals to 20, 35, 65, 80 composition had been used into 1 minus X B4C as TIC. Then, to prepare the porous preform, the mixed powder was formed by freeze drying of the slurry coming after with cold pressed. In flowing argon at 1400 degrees Celsius, the porous B4 TIC mixture was eventually sintered for 2 hours in an Al2O3 tube furnace. Secondly, the microstructure and phase composition. The phase composition was analyzed by X-ray diffractometer by using monochromatic CUK radiation at 40 kV and 40 milliammeter. Scanning electron microscope had been used to analyze the characterization of cross-sections of the cut samples that had been polished. Meanwhile, the elemental composition was examined with an energy dispersive X-ray spectrometer or EDS. Archimedes method had been applied to measure the open porosity and bulk density. Thirdly, the mechanical properties. The 3-point bending method and single-edge V-notch beam (SAVNB) method were used on a universal testing to dignify the flexural strength and fracture toughness. Next, as for SAVNB test, pre-cracking in samples was performed by EDM and consecutive razor blade notching with 1 micrometer. Vickers hardness is also measured on the polished surface of the samples by a hardness machine.
Density increased from 1.71 gram per cm cube to 3.16 gram per cm cube, and the open porosity decreased from 28% to 0 as the samples varied from B0.8 T0.2 to B0.2 T0.8. During the aluminium silicon melt infiltration process, boron carbide reacted with aluminium to form a ternary aluminium-boron carbon phase that acts as a barrier to aluminium-silicon melt infiltration and results in high porosity in infiltrated samples with a higher boron carbide fraction. All S1 to S4 samples show titanium diboride diffraction peaks at 2 theta of 44.53, 34.19 and 27.68 after sintering. Boron carbide was found in samples S1 and S2, titanium carbide in sample S4, while both boron carbide and titanium carbide were found in sample S3, indicating that their incomplete interaction during sintering could continue under the liquid path of aluminium-silicon melt. Due to the correct boron-titanium atom ratio of raw powders, sample B0.35T0.65 has the strongest titanium diboride diffraction peak. According to the EDS result of sample B0.35T0.65, spot 1, the elongated titanium diboride grain in area P1 is scattered in white faces form of titanium, silicon, aluminium and carbon elements, and its components are jointly validated on the basis of titanium 3, silicon, aluminium, carbon 2 determined by the XRD. The EDS result for spot 2 in region P2 shows that the components are also the same as P1. However, the two samples of B0.2T0.8 XRD results demonstrate that no residual silicon was found. As a result, the titanium carbide and aluminium in that sample were left superfluous. The highest flexural strength and fracture toughness are found in sample B0.35T0.65 that are 245 megapascal and 4.32 megapascal M1/2 respectively. The sample B0.8T0.2 has a relatively low flexural strength, which can be attributed to its high porosity. The well-distributed titanium diboride and silicon carbide particles in sample B0.35T0.65 act as barrier reinforcement, strengthening and toughening the material. Viscous hardness of sample B0.8T0.2 is the lowest because of its increased porosity, while sample B0.35T0.65 is the highest due to the presence of the boron carbide phase. Boron carbide has the highest viscous hardness of the four phases at 41 to 45 GPa. The viscous hardness of silicon carbide titanium diboride ceramic composites decreases as the boron carbide percentage in the raw powders decreases. The flat regions refer to infiltrated aluminium and silicon phases, while the rough regions refer to titanium diboride and silicon carbide particles in samples B0.8T0.2 and B0.65T0.35. Aluminium and silicon phases have a transgular fracture mode, whereas the titanium diboride and silicon carbide phases have an intergranular fracture mode. On the fracture surfaces of the infiltrated samples, grain pull-out of titanium diboride or silicon carbide is clearly apparent. Crack branch is also present in sample B0.2T0.8 except crack deflection. The ductile titanium 3 silicon aluminium carbon 2 phases in sample B0.2T0.8 show delamination and laminate fracture plastic deformation behavior, which promotes crack branch and consumes a lot of energy to prevent crack propagation. The amount of titanium 3 silicon aluminium carbon 2 in sample B0.2T0.8, on the other hand, was limited and clumped together as a cluster. As a result, the toughening impact of titanium 3 silicon aluminium carbon 2 phase is negligible. Microstructure and phase component of the composites were examined. When the weight ratio of boron carbide/titanium carbide raw powders was 35:65, silicon carbide titanium diboride ceramic composites demonstrated optimum microstructure and had the best mechanical properties. Lower comprehensive mechanical characteristics of silicon carbide titanium diboride ceramic composites resulting from hundreds of micrometers titanium diboride titanium silicocarbide aggregation structures occurred in the manufactured composites when the weight ratio of boron carbide/titanium carbide raw powder was 20:80.